Hi folks, here's the lesson and it's a tricky one today, so you need your thinking boots on. Are you sure you don't want me to wait for you while you go and get them? Oh, you've got them on already. Well done. In which case, yes, I know you want to crack on and get the job done. Let's do it. So, first of all, type 1, y equals ax to the n. Y is a variable and x is a variable. Y is actually depending on whatever x is. A and n are just constants, and we're trying to find what those constants are. Now, we're going to start with a simple example of y equals 2x cubed, so obviously we know what a and n are, but I'm just using this as an example to show you really the structure of what we're going to do. The graph of the function y equals 2x cubed looks like that. However, if we take logs of both sides, we end up with log y equals a log of 2x cubed. Using our multiplication rules for logs, we can split that as log 2 plus log x cubed, and we can bring that power of 3 down to write log y equals log 2 plus 3 log x. Okay? So if in that relationship we replace y for log y and x for log x, we end up with this equation. Y equals log 2 plus 3x. Now, because y was varying, the log of y will vary, so y is a variable. Because originally x was varying, log x will vary, therefore this capital X varies. So this now is a different relationship, okay, between a new variable called capital Y and a new variable called capital X. When we have a look at that relationship, we can see that it's saying Y is some constant plus 3 lots of X. And that's a linear relationship, that's a straight line relationship. And that is what the straight line would look like. Log 2 would be the y-intercept, and the gradient of that line would be 3. Okay, so if we just pause there and sort of say, well, what am I doing here? I'm taking that exponential, that curve of y equals 2x cubed, and by changing the variable of y and x, I'm now forming a straight line graph, and here it is. That's a straight line graph. And you might be thinking, well, why is he doing this? And the reason is this, is that if we, for example, carry out an experiment and we have our set of results which look like an exponential, by changing the variables as we have just done here, we will obtain a straight line graph, and we can use that straight line graph to find the precise relationship we're trying to find a, the constant a, and the power n. Remember what the original relationship was. It was y equals a times x to the n, and this is going to help us find a and n. You still might be a little bit unclear. It's all right. Pause the video, go get yourself a cup of tea, all right, because I'm going to do an example and I hope it become nice and clear for you. Please don't be panicking. So just to recap, y equals ax to the n is our original no straight line relationship. But if we take logs of both sides, there is a straight line relationship between log y and log x. Okay, so our original expression is this. We take logs of both sides and rearrange it to this. We then replace log y with y, log x with x, and we end up with this here, which is our straight line relationship. And it's by analysing this straight line relationship that we're going to be able to find A and N. Because log A will be the y-intercept on our straight line curve, and N will be the gradient. Okay? And what you can see in yellow are the highlights there. You probably, if you're summarising some notes, pause the video, because what you see in yellow is essentially what you need for your notes. And we're going to back that up with an example. And this is an example from the textbook. Okay, we've got a relationship R equals A P to the N. So remember, R is a variable, P is a variable, A is not, it's a constant, N is a constant, and our job is to find A and N. Have we got it so far? We're trying to find A and N. Now, you might think, well, why don't we just substitute some values in? So, for example, if we take the values of Birmingham, which is our second ranked city with a population of 1 million, then we end up with R, which is the rank, equals A times the population to the power N. And then if we do that for Leeds, our third ranked city, we end up with 3 equals A times 730,000 to the power of N. And if we divide those, we get on the left-hand side 2/3, and on the right-hand side we get this fraction, but in that fraction, the A's cancel. So we actually end up with 2/3 equals 1 million to the power of N divided by 730,000 to the power of N, which we can actually write as that. We can write the 1,730,000 as a single fraction. And then we can do our usual log stuff, and applying logs, we can actually find that N equals that. So we're able to, just by substituting those values, find N, and then we can go back and find A. N is negative 1.29, by the way. However, the problem with that is that we've only used two values in the data. We've only used Birmingham and Leeds. Okay, we've ignored all the other values. And what if Birmingham or Leeds' data wasn't quite accurate? We've factored in an inaccuracy into our result, which can actually give you a very significant error, as you are going to see. So in actual fact, we need a way of using all our results in order to find A and N. Because remember, any single one of these results could be inaccurate and we don't know. So even if we took Birmingham and Leeds, which you might be thinking, well, doesn't that cover the first and the last? Sorry, beg your pardon, Birmingham and Bradford. Way for Bradford. Taking the first and the last, doesn't that cover it all? And the answer to that is no, it doesn't, because again, one of those two bits of data could be inaccurate. Okay? So we need a method that uses all values. That's a relationship, remember. Taking logs, we get that, which gives us that, and then using the power rule, bringing the power down, gives us that. So now what we want are values for log R, and we want values of log P. Okay, and we're going to form that straight line graph. So we need log R, log P. Therefore, let's form a new table of values. When R is 2 for Birmingham, log R is 0.301. And when P is 1 million for Birmingham, log P equals 6. And then we go to Leeds. when r is 3, log r is 0.477, and when the population is 730,000, the log of p is 5.863. And we go through like that, through the table, completing the values for log r and log p. And it's these values now, that our new table, that we're going to use. If we plot our values y against x, we should get a straight line. And that is the straight line we get. And note that blue line that we have obtained, this blue line here, doesn't pass through all the points. It's a line of best fit, because that's always what you get when you have measured data, a line of best fit. Log A is the y-intercept. Remember, we have a look up here. This is a relationship, top right-hand corner. This is a relationship. So n's the gradient and log A is the y-intercept. Now we can see from the graph that the y-intercept is 6.2. So log to base 10 of A is 6.2, which gives us that, and gives us that value of A. And you find if you calculate the gradient, you actually get negative 0.67. If you remember, when we just used two values previously, our estimate for n was negative 1.29, so it's quite a significant error there. And that's how we do it, folks. We form up here a new table of values using the log of our original values. We plot the straight line graph, and then we look for the y-intercept and the gradient of our straight line graph. So to recap, note x is the base. You might think, well, that's obvious, but actually it's important to note that that makes this different from the type 2 that you're going to see. X is in the base here. We take both sides, logs of both sides, and we end up with this relationship, which then becomes a linear relationship, and it's a straight line where log A is the y-intercept and n is the gradient. And now, folks, I want you to turn to page 331. That's in the textbook. That's not in the PDF. Page 331 is in the textbook. And have a go at questions 2, 3, 5, 6, 9, because they are all type 1 questions. Okay? Best of luck, folks, with those. As ever, drop me an email if there's a problem. You might want to pause the video, because get those type 1s done before we move on to type 2.